Okay, today we actually want to start talking about what do we mean by this word quantum and why is it crazy in terms of the way that we view the universe. The craziness may not come until tomorrow, but let's get started with the term anyway. So we're going to be looking at the quantum nature of light. I want to remind you about the photoelectric effect. Light comes in, hits a metal, and the electrons on the metal get ejected with a certain kinetic energy. We did some studies of the photoelectric effect using a virtual program to simulate what scientists found in real life. We did things like change the color of the light. We changed the metal. We looked at how many electrons were flying through here by monitoring the current. Now, we didn't do it that way because we can see the electrons in this virtual program. We used a power supply to try to stop the electrons to find out how fast they were going and how much energy they possessed. What we learned from all this was that higher frequencies gave the electrons more kinetic energy. It did not go through the origin, but instead had a distinct starting point. Each metal had a different distinct starting point. That distinct starting point is called the threshold frequency. And you'll notice, even though they're different metals, they have the same slope. We saw that the slope of all of these was Planck's constant. We brought it down to an equation that looked like this. The kinetic energy is the energy of the ejected electrons. The HF, we said, was the energy of the light. And the work function was a property of the metal, how hard it was to get the electron out of the metal. We saw the brightness did not affect if they came off, but it did affect the number that came off. Okay, so these were all the things we learned about the photoelectric effect. Here's the problem. The old model of light is not consistent with the results of this experiment. So for instance, we used to think of light as a wave that came off of the object that was giving off light and spread out in all directions in a giant spherical pattern. As it got farther from the source, the light became less and less intense. So we would expect that if we put a metal target here and no electrons were emitted, we would think, oh, the light's just not intense enough to knock an electron off. Let's move it a little closer. The problem is, no matter how close we move the metal, if electrons did not come off at this distance, they still did not come off at this distance. It is as if the intensity, the brightness, did not affect the energy of the light, but that makes no sense. But it is consistent with the results of the experiment. So Einstein thought about it for a while and said, I've got a new model of light. Here is the way we are going to now view light. He's going to say, forget about the wave nature for the photoelectric effect, and instead treat light as if it is made up of particles. The strange thing about these particles is they have no mass. There's no actual matter, so they're not really particles. What they actually are is just a small bundle of energy. Somehow the energy is localized in a small little packet. It's oftentimes referred to as a quantum of light, the smallest individual unit of light. Nowadays, you'll hear it referred to as a photon of light. It's a small bundle of energy, no mass, and we call this a photon. Einstein said when the light is dim, that just means there's not a lot of photons. When the light is bright, it means there's lots of photons. If you were to compare a photon from bright red light and dim red light, the photons themselves would be identical. This photon is identical to that photon. They are both the same color. They're both carrying the same amount of energy. It just so happens that when it's brighter, there's more photons. It does not make the individual photons more energetic. How do you get the energy of those photons? Well, we use the familiar equation that we saw from the photoelectric effect, which is Planck's constant times frequency. It turns out that HF is the energy of one little bundle of light, one photon, one quantum. Okay, so energy is determined by what we would refer to as the frequency. Here's the old model, here's the new model. In the old model, again, light comes off as a wave. The wave spreads out into bigger and bigger spheres, so the intensity becomes less extreme. In the new model, the light comes out as a photon, one photon at a time, shooting off in a random direction. And the reason why it's brighter when you're close is the photons have a higher density. Not the photons themselves, I don't mean density like mass over volume, because there is no mass, but there's a higher density, that is photons per cubic meter. Out here, the photons are more spread apart, so the photon density is a little less. So brightness is determined by how many photons are present in a given space. Old view, we had light being determined by amplitude, right? The brightness of the light was determined by the amplitude. That is not correct. Brightness is determined by the number of photons, okay? Higher number of photons in a given space is going to be a brighter light. Regardless of whether it's bright or dim, it still travels at the same speed. Each photon has the same energy, and each of these photons is without mass. If you have a red photon and a blue photon, the red is going to carry less of a punch. It's going to have less energy. So blue photons have more energy in their bundle than the red photons. They're still going to travel at the same speed, and they're both going to be massless. It's just that the blue one has a bit more energy inside of it than the red. This idea of light being a photon helps explain when an electron falls from one level to another, according to the Bohr model. Light comes off. We now realize that one photon of light comes off. One electron falling produces one photon of light. Based on the energy gap between the two levels, that determines the energy of the photon. Okay, so a certain energy gap means a certain energy photon. If this gap is 3 electron volts, the photon will possess 3 electron volts. Very simple, very logical. We go back here and say brightness affects the number of electrons. Why? Because just like we said, it's a one-to-one relationship. Not just for the Bohr model, but also for this photoelectric effect. That means one photon knocks off one electron. So if one purple photon has enough energy to knock off an electron, then every purple photon has enough energy to knock off an electron. So each photon corresponds to a new electron. More photons, more electrons. Double the photons, you're going to double the number of electrons. You'll double the current flowing through that circuit. If one photon can't do the job, then 1,000,000 photons still can't do the job. They don't team up, they work individually, so it's a one-to-one relationship. If one photon can't knock off an electron, then regardless of how many you have, they're not going to be able to knock off the electron. Okay, so again, the formula, Ke equals HF. The HF refers to the energy of one photon. This refers to the energy required to pull the electron out of that metal, and the kinetic energy is what's left over. This is simply energy conservation. If this had 5 electron volts bursts of energy, and it took 3 electron volts to free the electron, we would have 2 electron volts left over. Start with an energy of 5, you end with an energy total of 5. Final thing I want to mention for today before we get into more of the craziness tomorrow is that these little bundles of energy that we call photons not just possess energy, but they also possess momentum. So we could actually shine light onto a really light object with a big surface area, and the light could actually push the object through space. This is known as a solar sail. We are using the momentum of light to give another object momentum. So, as a quick summary, we now view light as a massless particle, no mass, and yet it possesses energy and it possesses momentum. To get the momentum, you do this formula, Planck's constant divided by wavelength gives you momentum. And I want you to realize that these photons can hit particles, and just like if they were particles themselves, the light will interact just like a billiard ball hitting another billiard ball. It possesses energy, it possesses momentum, it hits the particle, it gives the particle some of its energy and momentum, and shoots off in the other direction. Notice how it changed color. Why did it change color? Because it lost some of its energy. It lost some of its momentum. This effect is known as Compton scattering. It's another proof that light is composed of these little bundles called photons.